As an example, let's consider the equation y prime equals t divided by 2. I've already sketched a y versus t coordinate system and put red dots at 9 points in the system, and the 9 points correspond to the coordinates listed here. I probably should have listed t before y, but we'll live with it as it is. Now we've got y equals 0, t equals 0. What's our value of y prime? Well, our value of y prime is t over 2. T is 0, so we conclude that y prime is 0. We're simply following this rule for calculating our slopes y prime. If y is 0 and t is 1, well, 1 over 2 is 1/2. If y is 0, t is 2, then y prime is 1. Now, you probably picked up on the fact that the value of y doesn't make any difference at all, because it's not part of the rule for calculating y prime. Could have been. It was in the first example, where I didn't tell you the rule at this point, but in this case, we've got the rule. It's y prime equals t over 2, and we're going to get a very simple pattern to our results here that you can easily verify. And this tells us that at the point 0, 0, where t is 0, y is 0, y prime is 0, so our slope is 0. So I'm going to indicate that just by drawing a kind of a heavy black line just a little above the t-axis so that we can distinguish it from the blue line. And then when t is 1 and y is 0, our slope is 1/2. Well, t is 1, y is 0 here. Slope of 1/2 is about like so. At t equals 2, y equals 0, our slope is 1. At t equals 0, y equals 1, our slope is 0. And we can see that anytime t is 0, so here, here, or here, y is 0. So that through these 3 points here, the points at which t equals 0, we get the horizontal slope line. Whenever t is equal to 1, we see that y prime is going to be 1/2, and that's very easy to see from the rule. So we're going to have a slope that's identical to the one we've already drawn. And then at t equals 2, our slopes are 1. And right here is a picture. I don't think I did those slopes quite accurately. The one should probably be a little bit steeper, but we get the general idea. And if we then pick any point to start with, estimate what the slope might be at this point, probably fairly low, and as we move on, we follow the lead of the slope field, we can get an approximate solution. Now we can do more than that. This equation y prime equals t over 2 can be easily solved. We can see exactly what these curves should be, and then we could compare the curve we've sketched with the curve as it should be. Y prime equals t over 2 means that the derivative of y with respect to t is t over 2. Now, if we integrate dy dt with respect to t, and if over here we integrate t over 2 with respect to t, we find that, well, the integral of dy dt with respect to t is just our function y. And the derivative, or the integral of t over 2 with respect to t is t squared. And of course we have an integration constant on both sides, so that by the fundamental theorem of calculus, this side will give us y. It'll actually give us y plus some constant. This side will give us t squared plus another constant. We just absorb both of those constants together, call the constant c. So that a solution to this equation is the function y equals t squared plus c. Now we could write that as y of t equals t squared plus c. Means the same thing, it's just that here we've written the specific t dependence of the curve, so that y of t equals t squared plus c is a function which, when substituted into this equation, gives us an identity. You should be able to verify easily that if we substitute t squared plus c for y here, y prime is going to be the derivative of t squared plus c. That derivative, good heavens, screwed that one up, didn't we? Y prime is t over 2. The antiderivative of t over 2 is going to be t squared over 4. Fortunately, I have room to write that in, and I'm going to go on. You see what happened by substituting this expression back here. I suddenly realized that I'd made a silly error in my integration, and that the equation did not satisfy, or that the function did not satisfy the original equation. Now that I've made the correction, y of t equals t squared over 4 plus c, we see that if we put this into the equation, the derivative of t squared is 2t, so the derivative of t squared over 4 is going to be 2t over 4, which is t over 2, which is identical to the right-hand side of this equation. The derivative of the constant is, of course, 0. So we see that we've obtained a function which satisfies this equation, and we call this function a solution to our differential equation.